So I'm Martin O'Reilly. I'm Director of Research Engineering at the Alan Turing Institute, which is the UK's National Institute for Data Science and Artificial Intelligence. And I run the research engineering group there, which is a team of research software engineers, research data scientists, and research computing engineers. And we work across the Institute's research program to help our researchers bridge that gap between research and practice. And today I'm going to try and give you a little high-level overview of large language models, and I'm going to talk about sort of what they are, how they work to some level, and give you a bit of a flavor of what they're sort of good at and not so good at. And again, there's going to be quite a lot of interactivity here, so if you could get yourselves on sort of Menti and sort of enter that code or scan the QR code. For the initial ones, it will also be at the top of each of the Menti slides. So let's start. What are our large language models? Well, I think an important thing, they're very big in the zeitgeist at the moment, but they're just one type of AI, and AI is a huge field, and data science is even bigger. And they sort of do one thing, which is predict the next word. I mean, strictly it's a token, but for today we'll say it's a word. But they do it very, very well. And they are very big. So, they're you're talking about sort of billions of parameters and sort of, billions to trillions of tokens of words that they're trained on. And you're talking, about them sort of dealing with somewhere between 2,000 and sort of 32,000 sort of previous words as part of their context. And GPT-3 was estimated to cost about $4.5 million to train, and GPT-4 is probably 10 times on all of those sorts of numbers. But even though they're trained to do this one thing very, very well, predict the next word, they actually can do lots of other things, and some things are maybe a bit surprising, and we'll talk a bit about that sort of later. And these last 2 points about being very, very big and being able to then sort of leverage that kind of one-off, what we call pre-training, that's very expensive, to then do some less expensive, much less expensive fine-tuning or transfer learning, is together what I think makes them an example of a foundation model. You can put this big investment in, and you can sort of apply it to sort of other areas. So we're going to do our first interactive thing here. So if you could all sort of get on Menti. We're going to do some human text completion, and the model's going to be sort of like this. I'm going to give you the beginning of the sentence, and you are going to put the handful of words that you think completes the sentence. I'll give sort of a few minutes here to sort of see get a decent number of replies up, and then we'll sort of unhide the results. So it looks like there's a couple of big sort of popular ones here, and a bunch of sort of smaller ones. Okay, I'm gonna. Oops, sorry, I've gone. Okay. So what are we seeing here? God darn it. Let me try and do it from. Okay. So how's that worked? This worked. Okay, here we go. So call me maybe, call me later, call me back, call me now, call me tomorrow. So lots of sorts of things you might do if you're talking on the phone to someone. So next one, it was the best. Okay, that one should be up on your screens now. Okay, cool. When we get to about 70, I'll start sort of showing the responses. Okay, again, we got some sort of big ones in the middle there, so sort of let's see, hopefully that will sort of filter through. Otherwise, I'll sort of go back and forwards. Okay. Okay, so it was the best time, the best day, the best night, the best thing ever, the best off times. Interesting, let's come back to that one in a moment. Okay, and let's do the next one. It was a dark. Okay, yeah, we're getting sort of faster on our fingers here. So it was a dark and stormy night. Okay, some people getting the theme here, I think. It was a dark night, a dark time, a dark day. It is the truth. Okay, that's a very long answer there from somebody. That's getting some additional votes there. But again, lots and lots of sort of different responses there. Okay, looks like so fewer people sort of got ideas for this one, but let's see where we are so far. So it is truth universally acknowledged. It's the truth, not a lie. It's a truth bomb. It's the truth, the whole truth. It's the truth about you. Okay. And for our next one, 2 households. Okay, again, sort of some long answers here. Okay, let's start taking a look at what people are saying. Okay, 2 households are better than 1. Bobble gobble, surprisingly popular. 2 households both alike in dignity. Okay, so and then sort of for our final one, once upon. Okay, sort of, yeah. Oh, wow. Okay, that's a very, very popular response there. Okay, let's take a look at what we're doing. Yes, once upon a time. Okay, so once upon a time in Hollywood, once upon a time in Mexico. Okay, so now we know it's books. So I'm going to just ask you to sort of have a go at the first 2 again, now that you know it's books. So if you were saying, call me, what would you respond? Okay, we're getting sort of a couple of very popular answers there. Okay, call me Ishmael. So, something that we hadn't seen in the first one, we now know it's books. We're now sort of jumping straight to kind of, what are famous first lines from books. And then the last one, it was the best. I mean, actually, we were pretty good at this to start with, so yeah, again, sort of a very, very dominant answer there. Yeah, it was the best of times. So these are all sort of lines from sort of very famous books, and when we were just given it sort of cold, we were a bit mixed. But as soon as we knew it was books, we were able to kind of jump straight to what we needed. And so we had that additional context. And now let's compare ourselves to the machines. So I'm going to show you sort of several generations of text prediction. So this is my Android phone. It doesn't do very well at this task. It gets once upon a time, which I think we all got, and it does a bit terrible on the rest. It's a bit like us, call me when you get home. GPT-3, which is approaching 4 years old now, and it isn't instruction tuned, so it's not a chat model, gets about 2/3 of them right. GPT 3.5, which is the chat model, and we'll talk about what that means a bit later, again, gets a slightly different 2/3 right, and GPT-4 gets most of them right. And interestingly, with the 2 chat models, if you put all of them in at once instead of just one by one, it will get them all right, although for GPT 3.5, you need to give it the most obvious one first. So again, you can see them kind of leveraging this additional context. So how do LLMs work? So this is going to be a high-level overview, so if you already know a lot about them, you're not going to learn much, but they're sort of doing this next word prediction, but what else goes into the mix to kind of make that kind of into a powerful model? So the first thing is we're representing the meaning of text, and we do this via something called embeddings. So we take these words and we put them into these vector spaces, just turn them into strings of numbers, and the idea is similar meaning words will end up close to each other, and words that have similar relationships semantically, in meaning will have similar relationships and directions in this vector space. So, king and man will be close together, and queen and woman will be close together, and king is to queen as man is to woman, so they have a similar direction and scale effect. They're kind of connecting them. Similar with verb tenses, walking, walked, swimming, sort of swam. And often these are kind of neural network models of some kind. And if you want to sort of learn more about these, over 10 years ago, there was this word to vec sort of thing, which is what started all of this, and that's what you should Google. The other key thing, we talked about the size of these training sort of data sets. They're kind of millions, billions, trillions of words. And it's really hard to get good quality annotated training data for this. So how do we solve that problem? Well, we do this thing where we take the internet, which isn't annotated, isn't curated itself, but has a lot of sort of reasonable quality text out there, and actually it's a slightly curated set of the internet. We do this thing called masking, where we take some words out and we tell the model, hey, predict this next word in the sequence. And when it does it, we can tell it whether it's right or wrong, and we can give it an error signal because we do know the right answer. We just hid it from it. And this is sort of self-supervised learning. And in terms of the data that goes in, it's most of something called Common Crawl, which is one of the big automated web crawls. It's most of the English language Wikipedia. It's some code, and we'll get to that a bit later, and lots of books, which is why we can expect these models to be quite good at the first line sort of problem. The next thing is they consider lots and lots of context. And so we talked before about sort of 2,000 to 32,000 kind of tokens or words of sort of history that they can think about when predicting the next word. And we did sort of all right at this, but we needed a little bit of a clue that it was books before we got really, really good. But let's say we'd started with this. So I'll just ask the people in the room to sort of shout out. If you're at home, just shout at your computer. Paul went to the bank to deposit a check. Absolutely. Paul went to school to sit an exam. Exactly. Paul went to the river to catch a fish. Right. And that last one, we might have said Paul went to the river to sit on the river, and we might have said bank, and we'd have known it's a different bank. And similarly, the models will sort of be able to distinguish so the bank that's riverbank and the bank where you put your money. I'm going to talk now about the real sort of technical innovation, which is this sort of transformer model you might have heard of. And one of the things it does is sort out how to handle this large context that the models are sort of dealing with. So at their heart, transformers are a type of deep neural network. And for those of you who don't know, I'll just give you a quick sort of overview of that. So these are sort of nodes in a graph that are connected to sort of nodes in this one's a feed-forward network, so all the connections are from the left to the right. The input layer encodes your kind of inputs, so it might be pixels in an image, it might be the words in a sort of sentence. There's hidden layers that kind of combine those in a bunch of ways I'll talk a little bit about at the moment. And then there's the output layer, which says maybe, is it a dog or a cat for an image, or what's the next word? And so each of these, sort of what makes a model deep is it's got more than one of these hidden layers. So that's not very deep, but they usually have more than, significantly more than one. And there's just this sort of weighted linear combination of all of the outputs from the previous network. And then there's this nonlinearity, and it's this nonlinearity that lets you learn sort of arbitrary sort of mappings, arbitrary sort of relationships between input and output data. And this is kind of what transformers look like. If you go to the Attention is All You Need paper, this is what you'll see. This is actually a little more complicated than we need just for text completion. So on the left side, you see an encoder, and on the right side, you see a decoder with a little bit extra in the middle to incorporate the output from the encoder. And really, the only difference between a decoder and an encoder is an encoder gets to see the whole sentence forwards and backwards when understanding what's important to a word, and a decoder only gets to see the past, the words that have come before. So we're not going to, when we just want to generate sentences, we're not going to need an encoder, and we're not going to need this thing called cross-attention, which is how the encoder content gets incorporated into the decoder. Later on, we'll touch on an example where we do need both, but for the purposes of this bit, we're looking at a simpler model, which is this. And I'm going to talk through sort of both how we use these and kind of what the different components are, again, at a high level. So the way you use one of these is a sort of word at a time. So you take the sort of beginning of your sentence, and you chuck it into this bit at the bottom, and out comes the next token. So a long time ago, you'll get in. Then you take that extended sentence, you chuck it in the bottom again, you get A, and you keep going till you get the opening line of Star Wars. And so this bottom bit is where we do our embedding, and that's just what we talked about before. We're turning words into sort of representations in this vector space, sort of just long strings of numbers where these vectors are similar to each other if the words have similar meaning. And we do this extra little trick of positional encoding, which is basically just tagging onto the beginning or the end, where is this word in the sequence in the sentence? And what that does is, without having to structure the network to be aware of ordering or space or time, you can sort of have it treat a word differently if it appears at the beginning of a sentence than if it appears in the middle or at the end. This bit in the middle is this key bit called attention. That's the title, attention is all you need. This is a decoder, so we don't see this top. This is just a relationship that says this, if you go down on the left, this sort of word in this sort of sequence a long time ago, what does it care about? What's important to it? What information from other words in the sentence does it look at? If it was an encoder, it would be allowed to look backwards and forwards, but it's a decoder, so it can only look backwards. The first letter can only look at itself. Second word can look at the previous one, and so on. And you see that mostly they use their information about themselves, but they also sometimes use a lot of information about another word sort of prior. And this is just a linear combination, so it's a sort of weighted kind of average, if you like. And then we sort of use usually a feed-forward network, but one of these neural networks to help us sort of learn a more complicated relationship, given that kind of weighted by importance sort of sampling of our past, of our context. What do we think the distribution of next words is likely to be? And then we sort of do this softmax at the end and say, OK, this is the word we're going to pick. And then the final thing, which maybe isn't sort of necessarily a design feature, but is kind of what makes it a foundation model, is we do this huge pre-training to kind of train that transformer. And then if we do sort of some fine-tuning, so this cheaper kind of post-training, we can sort of make it good at other things. And one example of this is instruction tuning, which is how we go from GPT to ChatGPT. So if you take the base model, and we're going to use the previous generation because we've got access to it, you say, how do I fine-tune a model? You get a lot of similar questions about it. If you do instruction tuning, you ask it, how do I fine-tune a model, and you get the answer to the question. And the way this sort of works is, for fine-tuning, you can either do supervised fine-tuning, which you do a lot, which is you have some pre-prepared inputs and outputs, questions and responses, or what they do for the chat one is they generate a load of these automatically, and they get humans to say which ones they think are better or worse, and that's called reinforcement learning by human feedback. Which you sort of might see, again, sort of mentioned when you're talking about it. So altogether, these things, many of which aren't sort of novel themselves, are what sort of get you the power of a large language model and what make them so good at predicting the next token and the next word. Now I'm going to sort of talk a bit about what these models are good at, some of which might be surprising, and what they're not so good at. So the main thing they're really, really, really good at is fluent text generation. And that brings us to our second interactive sort of session. So here, what we're going to do is a RSE-Khan literary Turing test. So you should see now on Menti the option to choose A or B. One of these is an excerpt from the actual book, so in this case, As You Like It. The other one was generated by ChatGPT. If you think the actual book is A, press A. If you think the actual book is B, press B. I'll give you a moment to read these, but hopefully they should also be coming up on your screens when you pull it up. And let's see sort of how we're doing. OK, so we've got 41 responses so far. So let's show the responses and see sort of what we're doing. OK, so we think by some margin that A is the real book, but we've got a decent minority who think that B is the real book. And A is the real book. OK, sort of well done us. Or well done you. I actually comprehensively failed at this task as part of our Pint of Science sort of outreach earlier in the year. OK, Lord of the Rings, same sort of story. If you think the real book is A, press A. If you think the real book is B, press B. OK, let's see where we're going there. OK, sort of, looks like, again, mostly we think A, but the decent majority who think B. In this case, the robot wins. OK, so far it's a tie. OK, so the next one is The Handmaid's Tale. Same as before. If you think A is from the real book, press A. If you think B is from the real book, press B. OK, let's see how we're doing with answers. OK, we're up to about 50, so let's see what we think. OK, so strong sort of preference for B here, and we're right. OK, so lots of fans of Margaret Atwood in the room, so 2-1 to the humans. The next one is from 1984. So again, if you think A is from the book, you should press A, and if you think B is from the book, you should press B. Okay, let's see how we're doing. Okay, we're up to about 50. Let's see sort of where we land. Okay, so most people think B by about a 2/3 majority, and robot wins again. So it's down to the final one to see whether or not this ChatGPT has passed our own RSEcon Turing test. So the last one's from Pride and Prejudice. Hopefully, it's a bit more widely known. It's the same story as before. If you think A was the real book, press A. If you think B is the real book, press B. Okay, we're sort of approaching 50 answers, so let's see sort of where we stand. Okay, so again, probably 2/3 majority think that B is from the real book, and we're saved. Okay, so well done, everybody. AI is not going to take over the world just quite yet. I think we see there that this sort of fluency is definitely one of the properties that large language models are very good at. But they're also sort of good at a few other things. And maybe one we might expect from something that's sort of trained on this language completion is they're really good at summarization. So you give it a big pile of text and you say, look, could you just pull out the kind of essence of this for me? They do a pretty decent job. Sometimes you have to worry about them kind of inventing plausible things that aren't from the text you've given it, and if you ask it for references, it'll often generate some very plausible-looking references that don't exist. But it does a pretty decent job, and it's good at the inverse as well. If you give it some bullets and say, hey, could you turn this into kind of a start of a 10 for me, it's pretty good at turning it into a sort of fluent first pager. It's sort of very good at translation, and we have to set it up slightly differently. So going back to that first picture, the use case in the original attention is all you need paper was translation, and in this model, the encoder is what has the complete sentence in the source language. So if you're going from French to English, that would be, j'aime la société d'RSE. And on the right, you've got what we talked about before, which is you say, hey, what is the first word I should put here? And in this case, the first word kind of can take advantage of the full French phrase when it sort of does it. And what this does in the middle, this cross-attention thing, this second multi-head attention, is it sort of takes in this sort of encoded sort of version of the source language, and it sort of conditions the probabilities that you're getting from the English text completion based on those. And then on the decoder side, you do just the same as before. You put the first word back in, you get the second word, and so on and so forth. And then hopefully what you get is a reasonable translation of the source language text. So reasonably good at code generation. And again, maybe that's surprising, but I guess code is a type of language, at least we would think so. And it turns out there's also quite a lot of code on the internet. And in fact, some specific code was also gone into the training data. And I'll come back to that a little bit later. Chess is an interesting one. So ChatGPT was terrible at chess. It sometimes wasn't even very good at making legal moves. ChatGPT 4 suddenly got very good at chess. They reckon it's got a ELO score of somewhere between 800 and 1200. So apparently it's beaten a sort of 700 chess bot, and it's kind of lost to a 1400 chess bot. I don't really know what any of those numbers mean, but it's definitely a better chess player than I am. But then again, if you think about it, maybe that's not so surprising. There's a lot of chess games on the internet written out in this BGM notation, sort of very sort of stereotypical. There's these tokens that represent the pieces and where they are. And there's a sequence of moves that sort of play out to show you how the game goes. And maybe a bit of supportive evidence for this is the models are surprisingly well in championship level games. But if you start playing like randomly, it rapidly gets disastrous and starts making illegal moves again. So sort of looks like if you get outside of the space of sort of chess games that it might have seen in its training data, it's kind of less good at extrapolating out of that than it is about interpolating. So what are they not so good at? Well, the big thing you've got to be wary about is making things up, this hallucination, this fabrication. And GPT-3 was sort of very bad at this, or 3.5. It would be sort of really fluent articulate text, but you wouldn't get very far through it before you got really jarred out by this like just obvious thing that was not true. And GPT-4's got a lot better at that, but my personal experience is it seems much more plausible when I don't know about something, and it's a bit less plausible when I know a lot about it. And again, that's improved over time, but it's difficult to tell if that's kind of the model's got better, or they've got better at sort of filtering out and sort of biasing it not to kind of respond sort of when it's unsure. And interestingly, ChatGPT 3.5 has gotten a lot better, which implies that a lot of this work has gone in sort of post that big pre-training and either in the fine-tuning or some of the other sort of filters and things that go on to sort of between the model and the output. This isn't new, right? This is something we see in machine learning all the time, but there's a huge bias in the training data. It's just a call of the internet, and that in itself is sort of hugely biased. It's got toxic content. They're doing their best to put sort of filters on, but it's you take some of these sort of models that sort of combine where you can generate images from text, and you sort of ask for pictures of professors, and you get old white men. If you give it a picture and you ask it to generate other pictures of you, you get very different pictures if you're a woman and if you're a man. And while this isn't new, you sort of go back to some of the earlier image classification. They were much, much less good at classifying non-white sort of humans than they were at classifying white humans. And even if you go to things like a soap dispenser that doesn't detect dark skin. So this isn't sort of new, but because these models are so accessible to people and they're so fluent and so plausible, I think you're sort of getting these biases are kind of having a much worse sort of like harm than previous, more obvious fake data. Another challenge is these are snapshots of public data. They take a huge amount of time and money to train, that kind of pre-training, so you can only do it so often. So the things the model knew about kind of go out of date. And there's ways you can sort of fix that. You can sort of combine live internet query data or queries against your own sort of private data set. And so one way to do that is something called retrieval augmented generation. I won't go into the details, but if you want to Google it, that's a good thing to Google. And Bing, for example, has a GPT-powered sort of version of its search engine that does this. It's got a knowledge graph, which is a more classic kind of representation of the internet, and it somehow combines that with the large language model to try and give you the best of both worlds there. Maths is a bit hit and miss. Sort of the GPT-3 struggled even with sort of addition. Sort of when you get to sort of ChatGPT-4, it's much, much better, but struggles with some things like is it a prime number or not. And interestingly, both of these models are much, much better at writing code that does maths than doing maths directly. And again, maybe that's not surprising. You look at a sort of algorithm we've written out to do maths, and it's basically algebra, and if you sort of relabel your letters in algebra, you turn all the x's to y's and all the y's to p's, the algebra still holds. If you take, a maths problem written out with numbers and you turn all the 8s into 5s, the chances are that mathematical relationship is going to be broken. So code can be maybe quite basic. So like I think there's, people I've talked to about this, and I'll ask you your own experiences at the end, sort of end up usually at one or other end of the spectrum. They either find it brilliant and they use it all the time, and it's just like a much, much better Stack Overflow, or they find it frustrating because it doesn't generate the code that they want and they've got to do a lot of work on the end. And so again, maybe this is an example of where the model is sort of good at the things it sees a lot on the internet. We see a lot of how-tos and a lot of kind of documentation sort of text, but maybe not a lot of production code. Or maybe it's an example of as with generating sort of prose, if getting from a blank page to something you can edit, if the cost of sort of editing is cheaper than the sort of cost of generating that initial pass, then maybe you're in a sweet spot. And if it's not, then maybe you're frustrated. And that could maybe be very different for different individuals. So non-text data is interesting. So originally, these models were very much sequence to sequence and text sequence to text sequence. And nowadays, there's models that will generate images and even videos from text. So you're starting to get these sort of multimodal models. But I think sort of something to sort of look at there is sort of what is the opportunity here for maybe sort of other types of structured data. So it's not very good with sort of tables or relational data or time series data. And so these are sort of whole classes of sort of data sets that these large language models themselves aren't very good at. But we'll talk a bit later about sort of how that might change. And a key sort of thing maybe to underlying a lot of these, what's it good at, what's it bad at, and why, is do large language models understand? So are they just blindly doing sequence completion, and that just happens to be good at a bunch of tasks, but ultimately they're just doing sequence completion? Or because they've seen all this data and they're very complicated models, are they somehow building some model, representative model of the information contained in that data? So do they have a, one way of phrasing this is, do they have a world model? And one way we can probe that is by asking some sort of tasks that we ask humans. So this is a set of what we call common sense reasoning questions. And 2 years ago, half of these were red. So 3.5, ChatGPT 3.5 wasn't very good, and certainly wasn't as good as a human at answering this. This is ChatGPT 4, and it gets all of them. So does that mean that it understands common sense reasoning? Well, sort of maybe, or maybe some of these have made it back into the training data, or sort of maybe we've sort of fed enough similar examples. And I have to say I haven't checked that this one's still right. So part of the problem is the model's changed underneath you. But here's an example that it was getting it wrong the last time I gave this talk. So I put a diamond in a cup. I put the cup upside down on my bed. Later I came back and I picked up the cup and I put it in the fridge. So where is the diamond? And the model says, well, you took the diamond was in the cup, you put the cup in the fridge, therefore the diamond's in the fridge. We all know about gravity, and we know that when we turn the cup upside down, the diamond fell out, and the model doesn't, or at least didn't when I asked it this question. So I think this is, and I come sort of into this a bit later, but I think this is a sort of key sort of thing. It's really, really hard for us to evaluate these models and understand what do they really understand and what's their performance. So I'm going to briefly talk about opportunities and risks, and then I'll leave you with a final question about your own use of ChatGPT, and I'll open up for questions from you. So I think the key opportunity is conversational interface. This is just a much, much more like fluid sort of way to interact. And this was a prediction the last time I gave this talk, that we'd start to see these as interfaces to Home Assistants, and I believe Alexa will now have this as a kind of premium add-on in the near future. Summarizing text or synthesizing text, summarizing text or expanding bullet points, I think that's a thing we can all use it for. Writing about things well covered by available data on the internet, so I think GCSE essays are somewhat toast in the near future. Other foundational models for other types of data, and I think this is a really interesting question. So not just if we take large language models, what could we apply them to, what other interesting types of data, or what could we sort of retrain as this sort of sequence-to-sequence kind of sort of idea, but are there other architectures that might allow us to take really, really large sort of data sets that share a common sort of property, so maybe it's time series, sort of forecasting data, maybe it's models that are well described by differential equations. Could we learn, do some common expensive training and get a sort of foundational model that we could then tune to particular use cases? And in terms of risks, talked about this a little bit before, the biggest one is mis or disinformation, there's bias and toxic content, and I think the really big thing that makes these models much, much worse than previous ones is it's harder and harder to tell it from reality. So just on the text side, I'm sure you all used to over the last few years seeing lots and lots of auto-generated sort of advertising clickbait, and you would go to it and you go, oh, this isn't what I'm looking for. And now it takes a lot longer to figure out that it's actually nonsense. And with these multimodal models, we're starting to see people being able to kind of do these deep fakes of image, video, and voice. And again, it's just really, really much harder. It's this fluency problem. It just looks real, and therefore it's plausible, and therefore it does a lot more harm. I think there's a real risk that these models are less capable than they appear for some of the things we're using them for, and I think we just don't know how to strongly evaluate how good they are at different things. And there's a big risk of mistaking sort of plausibility for sort of capability. There's a big meta problem of lack of transparency and centralization of power. 4.5 million for GPT 3.5. 10 times that for GPT-4, God knows what for the next one. There's a handful of usually big commercial companies who can afford to do this, and there's a big spectrum of openness or closeness for these models. And even with the most open models, we get the weights. Maybe we even get a good paper about how the training data was sort of collated, but it's just really, really hard to use that to kind of reason about sort of what these models would be good or bad at, or how they might have biases or encode misinformation. And then this one gets talked about a lot, this existential risk. Is our LLMs going to give us this artificial general intelligence, and is it going to take over the world, and are we all doomed? And I wouldn't have put this one in because we have traditionally said artificial general intelligence is 20 to 50 years away, and you ask us again in 20 or 50 years' time, and we'll say it's 20 or 50 years away. We may well still be in that moment, but we've got some serious people who are, on both sides of the fence. Jan LeCun is like saying clearly it's not. These LLMs aren't going to be AGI, and actually, we're sort of nowhere near it. But you've got Jeffrey Hinton, very firmly on the other end, sort of saying, hey, this is something we should be worrying about, like nuclear war. So those are sort of people who have a high reputation in the field. So I guess it's something to think about. Personally, I would sort of place my bet that we're probably still 20 years away. But more importantly, I think there's a lot of problems here and now, and worrying about these problems is kind of more important than these sort of future problems. So hopefully you've got a little bit of a flavor there at high level of what LLMs are, how they work, and what they're good or bad at. And the final thing I'd like to get from you is the last question on Dementi, which is sort of how useful have you found LLMs? So I'm going to ask you for your coding and non-coding work. How often do you use them, and how useful do you find them? The left side is I never use them, I find them useless. The right side is I use them all the time, and they're as good as me. So if you could have a go at filling that in, and I'll open up for questions.
Thank you.
So I've got the questions up on my laptop. I don't know sort of if that's sort of transferred over.
Yeah, except you have to somehow project that on the other screen.
Here we go. Perfect. It turns out I have a second desktop that I was unaware of.
So we'll start off with just going in rough order. How does LLM text generation stop? Does the model itself predict when the last token occurs, or is this externally imposed?
So sort of if we go back sort of very early on, what you do is you take some number of tokens, you put them in at the bottom, and what you get is the next token. And that's one iteration. And then you as a human, or you as the model underneath, do you mean when you are in the conversational model? Yeah, that's a good question, and I don't know the answer. Say that again? OK, so one of the things it learns to predict is, so the answer from the audience was there are stop encoding. So there are tokens it learns to predict, which are stop predicting the sentence or the answer to this question is done.
Okay. So when you were talking about risks of LLMs, what about energy usage?
Yeah, so that is a very good point. They are massive, and when you're talking about taking 6 months or 12 months on thousands of GPUs, that is an awful lot of energy, and GPUs aren't getting any more energy efficient. So I think that's a big problem. I think that's a big question for us is the value we're getting from these worth that sort of investment? But one of the things we do see is, yes, there's this next generation of model that gets better and bigger, but also people are training smaller models on maybe more curated data sets or sort of more constrained in their structure, and they're getting kind of close to sort of the results of the bigger models. So I think there's these two parts. There's the big training, which is super expensive, but you only do it once. And then there's inference. And we used to say that training was expensive and inference was free. And I think one of the things large language models are getting to the point of is that inference isn't free. So I think for 3.5 or 4, it takes like 4 A100s to kind of just run inference on the model. And yes, you can batch up lots of queries from different people to be more efficient, but even sort of using the models rather than training them is expensive. And but again, there's work to make models smaller and therefore more energy efficient. But I think that's a really useful sort of line of research in and of itself. I mean more generally, and there's several talks and sessions at RSECon this year on sort of green sort of coding and energy usage.
Also on the risks, are LLMs not doomed to a process of degradation as a result of being trained on their own future outputs?
Yeah, so that is, I think that is a huge, yes, I think absolutely. There's this argument that you've got sort of the pure, I mean, the internet's never pure, but you've got this unpolluted internet from before ChatGPT 3.5. One of the things that's happened is it's just become really accessible to the general public as well. So there's just a huge amount of generated sort of text getting out there on the internet. And when we see these, so there's a problem of it being polluted and therefore having lower quality training data. But there's also this problem of maybe overfitting, where the next generation of the model is trained on all of these examples of things the previous generation got wrong. And is it getting better at that thing, or is it just memorizing all of our test data? And when you see something be good at, say, pass the law bar and things like that, there are huge numbers of kind of practice tests on the internet. It's lots of kind of fact-based things. So I think we do see an example of that already in some of the things that we sort of see them be surprisingly good at. And I think that will just get worse as more examples of sort of things they're bad and good at sort of get overfitted with future generations.
Maybe the last one, can LLMs overfit like in supervised learning?
So yeah, I mean, I think I think one thing that we just don't know is to what extent they are sort of overfitting the training data when they get better at something. They use all of the sort of tricks that deep learning models do to avoid overfitting, so to do some regularization. So you get these sort of random dropouts and so on, and whether that's dropping out training data or dropping out sort of weights that you are going to choose not to consider when you're sort of calculating your prediction during training. So I think they're quite good at not sort of technically overfitting the large data set that they've got. But when it comes to, are we getting to the point where they're memorizing more and more things and therefore they're appearing better? I think that's the kind of real risk of overfitting, leading us down sort of an over-optimistic view of what they're good at.